Okay, thank you very much, Molly. Yes, I guess it's nighttime in Asia and beyond home time in Europe and Africa, and probably across the Atlantic. You're impatient for lunch, so I'll press on. I'll be presenting. So here's an overview, the content of this, an overview of respiratory particles, a lot of which was obviously covered by Stephen in the beginning of his presentation. The motivation for assessing the face mask material performance. Then an introduction to the AAC for those unfamiliar with it. I'll cover the face covering samples that we tested in their pressure drop measurements before moving on to the procedure for measuring the AAC classified particle penetration, followed by the data. And then I'll finish up with some ongoing work that we're doing where we're using a tandem AAC setup for characterizing the classification performance right towards the top end of the AAC size range. Okay, so the World Health Organization somewhat arbitrarily classifies aerosols as 5 microns or smaller and droplets as 5 to 10 microns in diameter. Both can be generated as a continuum during various respiratory activities, including coughing, talking, and singing. Obviously, the diagram on the right, which belongs to Steve, I have shamelessly stolen it, but it does very neatly distill quite a number of complex phenomena into one digestible diagram. So you see the yellow and green, these are the volume size distributions from coughing and speaking. Obviously, the larger mode dominated more by droplets, so they'll be settling on the surfaces relatively quickly. And as we move down the particle size scale, then there'll be more aerosol-like transmission with particles staying longer suspended in the air. So these are the wet aerosol size distributions. And that mode, that's between 1 and 10 microns, is particularly of interest for face covering filtration performance, with correspondingly high lung deposition rates plotted above. So face coverings have been widely worn in public spaces under many countries' COVID-19 laws and guidelines over the last year. And the intention is that the coverings will protect others rather than the wearer itself against the spread of infection. So the focus there is very much on filtering the exhaled flow. In contrast, the masks that are regulated are intended to protect the wearer. So it's of interest to investigate the particle size result filtration properties for various face coverings for both inhalation and exhalation flows and across a wide range of sizes. And we would expect from filtration theory that the collection of smallest particles down in the submicron scale will be influenced by diffusion. That's typically characterized by the mobility equivalent diameter of the particles, while collection of larger ones will be influenced by the interception and impaction mechanisms, which is where the aerodynamic diameter is more of interest. And additionally, electrostatic forces can be important, particularly in many of the regulated respirators, as they consist of electric media containing static charges to enhance particle collection. So this study uses an aerodynamic aerosol classifier to select monodispersed test particles by aerodynamic diameter. And we've got 3 groups of masks that we've tested: some regulated respirators, disposable surgical masks, as well as some cloth face coverings. So a quick introduction to the AAC. So that's the most relevant, aerodynamic diameter is the most relevant equivalent particle size for characterizing aerosol flow through filter media, since it relates to the relaxation time, which I'll define in an upcoming slide, of particles as flow conditions change. And the classification range extends from 25 nanometers up to more than 5 microns. The classified flow is truly monodispersed. So I mentioned that regarding, for example, the DMA, which is obviously a highly established method of aerosol classification, where there are charging artifacts to consider, and the high transmission efficiency reduces uncertainty in filter penetration measurements. So the AAC classifies particles by their relaxation time, so by a set ratio of sheath flow and rotational speed. The particles smaller than the desired size will remain entrained in the sheath flow, while larger particles will then impact on the inner wall of the outer cylinder. So the AAC can be thought of as translating the DMA into a rotating frame. So there's axial sheath flow and the drag force that the particle has to overcome, but the radial force is centrifugal rather than electrical. And that means there's a considerable advantage of there being no dependence on the particle charge state. So here's his definition of the relaxation time, the product of the particle mass and mobility. And it's also defined here in terms of a few relevant equivalent diameters, aerodynamic electrical mobility and volume equivalent. So aerodynamic diameter is the metric of interest where particle inertia dominates, such as respiratory deposition, atmospheric lifetime and settling, and particle collection by filters, cyclones, and impactors. This slide is referencing a previous study where back in 2018, where we looked at penetration particles through regulated filtering half mass. In this study, we classified the particles with the AAC and DMA alternately. So with particles classified by electrical mobility, then converted into aerodynamic space, and this was DOS particles. So you see the agreement here for this. This is a N95 conforming face mask, is very good, apart from a discrepancy at 150 nanometers. So to look at that further, you see on the top right slide, the 150 nanometers falls on the left-hand side of the size distribution we're using of the DOS. And that means multiple charges from the DMA are drawn over the peak. And we then step scan the DMA output with the AAC. So on the bottom right slide, you can see the single, the double, and triple and quadruple charges being resolved in that upstream scan. But downstream in the face mask, that solid red line just below, even triply charged particles are emerging there. So because we're bigger than the most penetrating size of the filter, where the interception mechanism is dominating collection, the addition of larger multiply charged particles is driving down the penetration result that we get from the DMA. So this just shows that care has to be taken when there are charging artifacts, when you're making precise measurements of filter penetration. So for this study, here there's a group of 3 EN149 masks conforming to the FFP1, 2, and 3 classes. So they have to conform to penetration tests with salt and paraffin oil challenge aerosols and meet certain filtration efficiencies listed here. And some optical micrographs showing the microstructure, which, as you can see, are a mat of randomly oriented fibers, generally around 10 microns in diameter. And that creates a very tortuous flow path for the inhaled and exhaled air to help enhance particle collection. And then a couple of surgical style masks, one composed of polyethylene and one polypropylene, which is certified medical grade. We're not comparing the 2 materials side by side. These are from completely different manufacturers. But again, you see with the optical micrographs, these are the melt-blown filter layers in the middle, because there are 3-layer masks. Again, randomly oriented fibers, more open fraction versus the regulated respirators. And then lastly, a couple of cloth face coverings. So a cotton one and then a polyester elastane blend. And you can see here the airflow is going through perforations, because what's happened is, while the individual cotton fibers are around 10 microns in diameter, they're bundled into yarns that are interlaced. So that means the aerosol particle interaction is more likely to be with those 100 micron thick yarns rather than individual fibers. Having said that, there are sort of frayed fibers that you can see extending across the gaps, which would help enhance particle collection. And then the polyester elastane, you see a more complicated interlooping structure, which gives it a more stretchable property. But again, the interaction is going to be controlled by those yarns rather than individual fabric fibers. So tests were conducted for filter face velocities corresponding to 30 liters per minute and 95 liters per minute for inhalation, and 160 liters per minute for exhalation through the entire mask, which is specified in EN149 for steady state breathing resistance tests. And what we've done is we've assumed a mask area of the mouth and nose of 160 square centimeters. So that conveniently falls out as face velocities of 3, 9.5, and 16 centimeters per second. So we're testing all the material samples at the same face velocity. And these are the pressure drop measurements. This is in Pascal on the y-axis. Just incidentally, for the FFP3 class, 300 Pascal is the limit for the 160 liter per minute, so that just comes in underneath. You can see the disposable surgical mask, generally more breathable, although actually the Reldine one is actually pretty similar in the flow resistance as the FFP1 on the far left, and then the far more breathable fabric, woven fabric masks on the right-hand side. So here's the procedure for the filter penetration experiment. So circular samples were cut from the mask and sealed in a 47mm diameter filter holder. A blank correction was applied to, so particle losses were characterized in the filter holder without the face mask samples. So that was largely negligible, apart from the largest particles at the highest face velocities, where there was a little impaction loss in the support grid. The procedure is consistent with ISO 16900. So there's a 3-minute stabilization time in particle free flow, and then the short-term penetration takes an average over the first 30 seconds of particle loading. And with the AEC, we maintain a constant 10:1 sheaf to sample flow ratio, and we're classifying particles with aerodynamic diameters between 50 nanometers and 5 microns. So across that range, we use the same classifier, but we do have to use 2 different DOS aerosol sources and 2 different particle counters. So I've summarized that in the table there. So it's the Collison and a CPC up to 2 microns, and then overlapping from 1 micron, then extending up to 5 microns with a Topaz SLG 250 and a Pallas Wellas, which I show on this slide. So the Topaz SLG is a condensation aerosol generator. Again, we were using DOS vapor. You can use waxy solids as well inside it. And that condenses the DOS vapor onto salt nuclei, producing monodispersed particles. I had to use a custom mod to further reduce the salt nuclei concentration, just to ensure we can generate particles right up to 5 microns in diameter. And despite its monodispersed output, we still pass the output through the AAC to classify at that constant 10:1 sample sheaf flow ratio, and also to make sure we're eliminating an additional small size mode of homogeneously nucleated DOS, which does appear when you brought down the salt nuclei concentration to a certain level. You will then also generate some homogeneously nucleated DOS particles, which the AAC will then eliminate. And then the Pallas Wellas, so that's output in geometric particle size obtained from single particle scattered pulse heights. So the relationship between pulse height and scattering cross section is determined with a calibration using latex particles. Particle size then calculated using me theory and corrected for the refractive index of the test particles we're using, which is 1.45 for DOS. So we're using that in the 0.2 to 10 micron size mode, although we are primarily using this as a total particle counter. So here's particle penetration data for all the face mask samples, starting at 3 centimeters per second. You see there are large differences between the groups of face coverings, and the cloth filtration efficiency is generally poor, is poor at the submicron size range. So that's because the interaction of particles are with the yarns rather than the individual fibers. As expected, the regulated respirators show excellent filtration efficiency, so which is why I've reproduced the graph on the right with a log y-axis just to show those. As we increase the face velocity, this reduces the timescale for collection by diffusion and electrostatic forces, so it tends to push up the penetration in the submicron range, and again at 16 centimeters per second. However, with the cloth face coverings, again, it is necessary to extend right into the microscale and have the equipment to do that to determine where they start to show good filtration efficiency. We actually see, and I've plotted it separately here, with the cotton and the polyester elastane on the right. You see with the solid lines for the high face velocity, we're seeing greater collection in that supramicron scale. So that's clearly the evidence of particle impaction, then enhancing collection by the interception mechanism. So we can characterize the trade-off between the filtration and the pressure drop using what's been called a figure of merit or a quality factor. So that's the log of the penetration divided by the pressure drop. And a useful property of that is that the value would be around the same for single or multiple layers of the same filter. So you can see the regulated respirators are all grouped together here. So in this chart, the further up the y-axis you are, the better value, as it were, you have for your face mask material. And as we push up with face velocity, obviously that value comes down, and we see the FFP2 and 3 staying very close together, which would suggest that the microstructure of those is the same, and that the FFP3 is actually just a thicker layer of filter. And we see the surgical masks sort of bundled together at the high face velocity once we've diminished the action of diffusion in the submicron range. And then finally, to finish off with some ongoing work. So the classification performance of the AAC using a tandem AAC setup. So previously, Tyler Johnson and co-author was published in 2018 on characterizing that at both low flow and high flow up to 2.4 microns. So from that analysis, this is assessing the transmission efficiency, which scales the error under the transfer function, and the transfer function width factor, which scales the full width at half maximum. So they're determined by scanning the monodisperse output of the upstream AAC with the downstream AAC, and then performing a deconvolution. And this was the data that was published at the time. So on the left, with the transmission efficiency, see that's plotted at low and high flows in comparison with the DMA and neutralizer. So the transmission efficiency of the AAC is much higher than you get with the combination of the neutralizer and DMA. That's not to say that there's significant losses in the DMA column itself. That's actually a consequence of having to use a neutralizer to prescribe the equilibrium charge distribution. So obviously the DMA is outputting singly charged particles, either positive or negative, and you're having to necessarily discard all the other charge states. And then the AAC broadening results on the right. So the transfer function is actually broader than predicted by theory, which is possibly due to flow effects in the rotating classifier. And in practice, the user could compensate for this by simply reducing the sample flow relative to the sheaf flow. So the high flow results are highlighted in yellow because they're of interest here. So at the time, that was using a DOS aerosol from a Collison nebulizer to look at 0.3, 0.6, 1.2, and 2.4 microns. So current efforts involve swapping in the Topaz SLG condensation aerosol generator in place of the Collison nebulizer, and swapping a CPC for the Palazuelos to then characterize high flow AAC classification performance at 2.4, 3.1, and 3.9 and 5 microns as aerodynamic set points. So this is ongoing work, which is involves a lot of repeated scans. And so far for 2.4, 3.1, and 3.9, we've been able to repeatedly show transmission efficiencies between 0.7 and 0.77 using the tandem AAC with OPC setup. And that includes after exchanging the two AACs. And at 3.1 and 3.9 microns, I've just included some examples from that analysis showing that transmission efficiency about 0.75. So on that, I'd like to just give some conclusions. So characterization of face mask material performance requires instrumentation capable of handling a broad size distribution representative of respiratory aerosols. Data were presented for monodispersed particles between 50 nanometers and 5 microns, which covers almost the full size range of the AAC for various types of face coverings. So regulated respiratories and the surgical mask comprise matrices of randomly oriented fibers. So that gives tortuous airflow paths that help enhance collection by diffusion and interception mechanisms. Whereas the cloth face coverings, the interaction of the aerosol particles is more controlled by the yarns or the bundles of fibers rather than individual fibers. So the filtration efficiency is generally poor at submicrons. However, as you move into the micron scale, you can see that most at 5 microns are collected. And the AAC transmission efficiency and transfer function width are currently being characterized for particle sizes up to 5 microns using a tandem AAC setup. And with that, I have overrun. I apologize for that, but thank you very much.
Thank you, Simon. Yes, very interesting work. And you do have a few questions. We do have a couple of minutes. And so we will start off with an anonymous question. Have you seen any plastic particles from the mask material itself?
Have I seen any, sorry?
Plastic particles from the mask material itself?
No, I imagine we would, because Hadley we're using the Pallas Welles as a counter, but obviously we have the live size distribution. So that's just rigidly coming out as a monodisperse thing on screen, and we're between 200 nanometers and 10 microns. So I haven't seen any evidence of any other types of particles or size distribution modes emerging there.
And then Steve asks, there are so many cloth materials. Do you have any suggestions on how to standardize testing, reporting, and making cloth masks?
Yeah, so that's a good question. Obviously, during the pandemic, and particularly in regards to fit testing, which is important for the regulated respiratories and for frontline healthcare workers, but for the general population, using these surgical style masks and cloth face coverings, either bought in supermarkets or homemade, yeah, fit testing is clearly not feasible, and poor fit will dominate particle exposure. And with that in mind, it is best to actually focus on more breathable materials rather than look at high pressure drop, high filtration efficiency materials to mitigate a little bit more against the leakage that will occur. So any material really, and we showed in the presentation, the problem with the cloth face coverings is that the interaction with the aerosol particles appears to be dominated by these bundles of fibers. So any sort of more knit pile types, which have more frayed fibers and can bring about more tortuous airflow paths, are going to help quite significantly.
Greg then asks, nice study, or he says nice study, and asks, is there a need to evaluate penetration above 2 micrometers? It seems all types of masks, even cloth, filter effectively for large sizes.
Yeah, so the experiments I showed where we exchanged the collagen and CPC for the Topaz SLG and Pallas Welles, we only extended up the size range for those cloth face coverings because I think even with the surgical style mask you saw at 1 to 2 microns, we'd already dropped far below 5% penetration. So while you might be able to ascertain the most penetrating particle size at the submicron level, I think it's still important to know where you're filtering at least more than 90% and extending up the microscale to properly characterize the performance of those materials.
Great, thanks. We kind of have the last 2 questions somewhat related. Martin asks about the efficiency over time, if there's a pressure drop due to loading of the filters. And Anne asks if you've taken into consideration the effects of humidity and the filtration efficiency when the mask gets wet.
Yeah, great question. So we were, I was mindful of the humidity effect. We were using zero air as the makeup air in order to, obviously that's certified to contain a low content of water to keep relative humidity low. So I know from previous studies and even my own that using salt particles you can get soaking and deliquescing from the bottom of the filter sample if you're not careful with that. So yeah, and this study was very much focused on the interaction of the particles with the clean filter medium rather than any sustained loading, but certainly that's an important area of investigation.
Great, thank you very